Hello everyone, this is Manny Dakal, and today I'm going to briefly discuss about the conditional expectation and the Haar basis. Conditional expectation and the Haar basis. Okay, actually, what is this conditional expectation? So you might have seen this. This in the probability, yes. So is from the name. We deal with the probability measure here. So let's consider a probability measure. There's omega summation and mu be a probability measure. And summation sigma dash sub sigma algebra of some sigma. Okay, so given f belongs to L1 omega summation mu, we define, let's define a sign measure. Nu on sub sigma algebra is nu of E equals integral over E f d mu, where this E belongs to the sigma's sub sigma algebra. Okay, so here is notice that is mu of E equals 0, then nu of E also equals to 0. Yes, so here nu is absolutely continuous with respect to mu. Yeah, so by the Radon-Nikodym theorem, there exists a unique function okay, let's call it psi. This is unique up to the measure 0, and this psi belongs to L1 mu, such that nu of E equals psi d mu. Okay, so as we can see, we can equate this. So this implies nu of E f of d mu equals psi of d mu. So here E belongs to sub sigma algebra sigma dash. So this unique psi is called this unique function psi. This unique function psi is called the conditional expectation. This unique function psi is called the conditional expectation of f on the sigma algebra sigma dash, and we denote it by okay expectation of f condition on sub sigma algebra summation dash or the sigma dash sigma prime. Okay, now this can be equivalently can be written with the characteristic function is equivalently. So this can be written as psi of characteristic E expectation of f characteristic E. Okay, so now if it consists of some countable many disjoint atoms, then it seems the expression for this is somehow a little simple. It takes this form. Okay, where if this is union and running from 1 to infinity air and they are disjoint. Okay, if they are disjoint, then this takes the conditional expectation can be expressed in this way. Okay, so recall some very fundamental properties of the conditional expectations, that is properties. Some of them are used in the proof. Okay, so if f is independent, if f is independent of sigma dash, then expectation of f given sigma dash or the summation dash yes that is equals to expectation of f. Okay, that is if f is independent of this, then expectation will be same, conditional expectation and the regular expectation will be same. So this is one of the property, a usual property that we are mostly familiar. So now if we have sub sigma algebra, suppose this sigma double prime is a subset of sigma prime is a subset of omega, then expectation of f given sigma double prime is equals to expectation of f given sigma primes given sigma double prime. So we call this the Traor rule. Similarly, conditional expectation is linearity, that is expectation of alpha f plus g given sigma prime equals alpha expectation of f given sigma prime plus expectation of g given sigma prime. So this is the linearity. And monotonicity, that is if f is less or equals to g almost everywhere, okay, then expectation of conditional expectation of f given sigma dash is less or equal to expectation of z given or the conditional expectation of z almost surely. So these are some properties that we are familiar with. So now let me recall some more. Okay, if f belongs to LP mu for 1 less or equal to p less than infinity, and z belongs to LQ omega summation dash mu, where 1 over p plus 1 over q is 1, yes, then expectation of the conditional expectation of f times z is equals to z times conditional expectation of f, and integration of c d nu equals integration of d e integration over e f g d mu, where this e belongs to the sub sigma algebra. So these are some facts or some properties that we can observe here. Okay, so now let's consider a lemma. Let's observe a lemma. So lemma 1, in the probability space omega sigma mu, this is a probability space where summation dash sigma dash is a sub sigma algebra of omega. Sorry, yes. Then for any one, for any f for any one less or equal p less than infinity, expectation of the conditional expectation is a norm 1 a linear projection from ELP to onto LP omega summation dash mu. So this is a norm 1 linear projection. Okay, so next, so keeping this in mind, like LP omega here, for this should be closed. Okay, and we observe that closeness also there in the that is I have done that is on the file. Similarly, we discuss a definition. I will put a definition there. In this definition, I think we are familiar with this definition. That is the Haar system. So let me recall this. The sequence of function on 0, 1 is considered a sequence of function Hn, and from 1 to infinity on 0, 1, and that is defined by H1 equals 1 and Hn of t equals 1 minus 1 0 if t belongs to 2s minus 2 comma 2 power k plus 1 comma 2s minus 1 2k plus 1. Similarly, minus 1 if t belongs to 2s minus 1 over 2k plus 1 comma 2s over 2k plus 1, and 0 if otherwise. And here n equals, for n equals 2 power k plus s, where k is from 1 to k goes from 1 to 1 0 1 2 and so on, and s runs from 1 to 2 power k. Okay, this is the Haar system, and there in our class, yeah, we observed that the Haar system and the constant for the Haar system is like 1s. Okay, so now let's recall some theorem. This is the partial converse of the Banach-Estenhaus theorem. So let Sn be a sequence of operators from a Banach space X into a normed linear space Y, such that supremum over n Sn is less than infinity. Then if t approaches to, if t from x to y is another operator, yeah, the subspace and the subspace X belonging to X, so that Sn of X minus Tx converges to 0 in num is norm closed in X. So this is a theorem that we are going to use, and similarly we have a proposition. A very applicable proposition here. Suppose Sn from X to Y n belongs to natural number is a sequence of bounded linear projection on a Banach space X into sorry, bounded linear projection on a Banach space X such that dimension of Sn of X equals n for each n Sn Sm equals Sm Sn equals S of minimum of m comma n. Okay, for any integers m and n, and Sn of X converges to X for every X belonging to X, then any non-zero sequences of vectors Ek, k running from 1 to infinity in X chosen inductively such that this E1 belongs to S1 of X and the Ek belongs to Xk of X intersection Xk minus 1 inverse of 0 if k greater or equal to 2 is a base for X with partial sum projections Sn n from 1 to infinity. Okay, so this is a proposition, and this proposition and the partial converse of the Banach-Steinhauer theorem that we are going to use in the proof of a proposition. So let's start to the Haar system. This is the main thing that I'm going to prove. The Haar system is a monotone basis in LP. Here LP is 0, 1, okay. For 1 less or equal to p less than infinity. Okay, let me prove this in brief. So here we consider a increasing sequence of sigma algebra, let Pn, and from 1 to infinity is an increasing sequence of sigma algebras that are contained in Borel sigma algebra of close interval 0 comma 1, and let they be defined. Let define B1 be the trivial sigma algebra phi 0 comma 1 close interval 0 comma 1, and for the n equals 2k plus s, where is previous the k is going from 0 to infinity and 1 is lesser equal to s lesser equal to 2k. Okay, let bn script bn be the finite subalgebra of the Borel set. Subalgebra of the Borel sets of 0 comma 1 whose atoms are dyadic intervals of the family script fn equals j minus 1 over 2k plus 1 to j over 2k plus 1. This is for j equals 1 to 2s, and from j minus 1 to 2k, j over 2k, if j equals s plus 1 comma dot dot to 2k. Now for each so for each n, let epsilon n denotes the conditional expectation operator, conditional expectation operator. So this is also an operator on the sigma algebra Bn. So by the previous lemma that we discussed, so therefore by the lemma that we just discussed, epsilon n is epsilon n, sorry, En, our expectation of n, is a norm 1 projection from LP onto LP01 on the sigma algebra Bn, and the space, where this is the space of the functions which are constant on the interval of family script fn. So these are constant on the intervals of this family fn. So let's denote that by LP Bn. So let's denote this by LP Bn. Now here, so we use this proposition. So we're going to use this proposition like dimension of Sn of x equals n. So it's like that, like this. So this is a this has a rank n. Okay, so here rank of expectation of n is n. Similarly, it satisfies this property also. This one is satisfied. 2, expectation of n, expectation of m. This is same as finding the expectation of m, expectation of n. So the expected minimum of m comma n for n2 positive integer. Yes. Also the set. So if you consider the set, f belongs to LP, so that expectation of n of f minus f of norm p converges to 0. Also this set is closed by the partial convergence theorem, by the theorem that I discussed. Yes. Okay, partial converse of Banach-Steinhauer theorem. Okay, also see it contains the set K running from 1 to infinity LP BK, which is dense in LP. Therefore, expectation of norm of expectation of n of f minus f p norm of expectation of n of f minus f converges to 0 for all f belonging to LP. So by the proposition, okay, so by the proposition that we discussed, that I wrote earlier, yeah, so that has the dimension s. So by that proposition, by the proposition previous, LP has a base whose natural projection are epsilon n. So this sequence is now the natural projection of this LP, okay, at the base. So LP has a base whose natural projections are this. So now also observe that also expectation of m of Hn, this is Hn if m is greater or equal to n. Okay, also observe this. N equals 0 if m is less than n. And as we discussed in class, when Professor introduced the R basis, so the time we discussed that the basis constant supremum over n, expectation of En, this equals 1. Okay, is this constant k equals 1, then we call the system is monotone basis. Yes, therefore the R system is a monotone basis in LP where 1 is less or equal to p less than infinity. Okay, this is all what I want to do today. So yeah, I did a little hurriedly anyway, so I hope you will understand the materials that I presented here. Okay, happy Thanksgiving. Stay safe. Thank you.